Hello, everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In the previous lecture, we discussed the underlying logic behind how the Hubs and authority centrality measures work. So in general, we assign to every node two different scores. One would be its Hub score and the other would be its authority score. So what is the exact algorithm that we can use to implement the logic that we discussed in the previous lecture? So that will be the focus of today's lecture. Let's get started and let's try to understand that a bit better. We'll start by doing a quick recap of the Perron-Trevini theorem for primitive matrices. It will soon become clear why we are doing it. For primitive matrices. Given a primitive matrix, P, then the following results always hold. So what are those results? First is P has a dominant eigenvalue which is the dominant eigenvalue itself has a few properties which is first of all simple, meaning it's the only eigenvalue equal to that value. So let's call this some lambda d, or lambda generally also written as lambda p, referring to the Perron root. So this eigenvalue has to be strictly simple, positive, and strictly larger in magnitude than that of the other eigenvalues. These are the properties that the dominant eigenvalue satisfies. So just to give you an idea, say if suppose my dominant eigenvalue lies, it's a positive number. One more thing has to be specified here. It is also real valued. By positive, anyway, clarifies it. So let me not repeat it, but obviously it's a positive number, so it's real valued as well. Now, every other eigenvalue that is there will strictly lie inside this disk. None of them can lie on the circumference of it. So this, for a primitive matrix, such a property always holds. And what does the corresponding eigenvector satisfy? So if the eigenvalue has such nice properties, then the expectation is that the eigenvector also might have some nice properties. So, of course, it does have, which we have discussed in more details before, but just quickly summarize the properties it has. Let's write it. The corresponding left and right eigenvalues let's call them WP and some VP. Sorry, I meant eigenvectors. The corresponding left and right eigenvectors associated with lambda p. Let's write lambda p. All the entries of the same sign. What would that mean? It would mean that if I'm now constructing VP, if VP1 is positive, VP1 greater than 0, meaning the first and keeping first, would imply for every j, VPJ is also greater than 0. And the same holds for WP as well. Again, how are primitive matrices associated with graphs? Let us say P is the, write it here, yet another small recap before we move into the main theme of the lecture, is that if P, the primitive matrix P discussed here, is the adjacency matrix of a graph of a diagram, say to give it as general as possible, then let's write a diagram G. Then G is always two things. First, strongly connected. This is the first property that it satisfies. And the second is that G is aperiodic, meaning whatever cycles there are in the graph, all of their lengths must have a GCD equal to 1. Again, let me remind you very quickly. This is a very simple graph. We see that there are two cycles here. First, and this is the second one. L1 and L2. If these are the lengths, then GCD L1, the length of this is equal to 2, and the length of L2 is equal to 1. So together, their GCD is equal to 1. Okay, now let's move to the main theme of today's lecture. So we'll continue our discussion on the hubs and authorities in reality, or the HITS algorithm, and now we'll try to figure out when does the HITS algorithm converge? Does it even converge, first of all? Let's again look at the HITS algorithm. According to HITS algorithm, V was the authority scores of the nodes. Right? Authority score vector. And U, on the other hand, is the hub scores vector. Having said this, what does the algorithm say? How would we go about calculating V and U? Is this. As per the algorithm, the authority score vector is given by this way, A transpose into U, and the hub scores vector are given by A into V. Slight rearrangement. So let's say if we rearrange it slightly, not really rearrange, we can say further simplification gives V equals A transpose times U. Now U, in the place of U, I can substitute this. So I can write A into U, and I can obviously replace this with A into V. Hence, V equals A transpose A times V. Similarly, for U, I can again substitute the value of V from here. So I'll directly write the main equation, that's equal to A times V, which is equal to A times A transpose into U. So now we see that the equations of the equations of V and U are now decoupled. So when can we say whether these two equations will actually converge to fixed values? So we get two different matrices of interest to us. One is A transpose A, the other is A transpose. Now let's write down a few points which will help us arrive at some conclusive answers to when convergence will happen. So we can say that additionally, obviously, A transpose and A transpose A are both symmetric matrices. Which would mean that okay, and notice that they're both symmetric matrices and are also real valued, which also follows obviously. Then it can be shown easily to some algebra that the spectrum is also real valued. Right. The eigenvalues are also real. So real symmetric, to sum it up, a real symmetric, any real symmetric matrix, in fact, will have eigenvalues which are all real. So now, again, we know that the matrix has real valued eigenvalues. All that we need to understand is when the conversions will happen. So the conversions can happen in this manner. If we additionally impose the constraint that the matrices are now also primitive. Further, our algorithm says that V equals A transpose A times V, meaning V is an eigenvector of transpose A. Similarly, U is an eigenvector of A transpose. We get it from these two expressions. When can we say that it would converge? The answer to that is if the matrix is primitive. In that case, we know that the powers of positive matrices always converge. So we have talked about how the powers of positive matrices evolve. We have talked about it in several occasions. Most recently, when we were trying to analyze the conversion properties of the averaging process. So again, if we apply the same thing here, then we know that the the solutions of these two equations always converge, and they converge to the eigenvector, but they also converge to the normalized eigenvector. So again, we have discussed plentifully in the past what is a normalized eigenvector. So in this case, all that we do is we construct, so let's call the normalized eigenvectors as Vn and Un. Okay. Now, the sum of all of the entries of Un and the sum of all of the entries of Vn must always add up to 1. In that case, we know that it satisfies the normalization process. Now, let's write up our main result. It says that we now make the assumption that both A transpose and A transpose A are primitive matrices. This is our assumption. Then, suppose, as we can always compute and the values of V as we can see here in an iterative manner. The new V is A transpose A times the old V. Hence, what we get is a sequence of the values of V. So let us say the sequence is given in this manner, V1, V2. Finally, it moves towards some Vk. Is the sequence of authority scores. Authority scores vector. The normalized sequence is given by the n1, the n2, and up to it goes up to some vnk, where k perhaps tends to infinity. Then the normalized sequence converges the eigenvector, normalized eigenvector again, corresponding to the dominant eigenvalue, eigenvalue And again, so note that corresponds to the eigenvector. Let's write the eigenvector is equal to some VP, meaning the Perron eigenvector, which is the dominant eigenvector. And if we write it VNP, it would mean the normalized eigenvector. Then this sequence here, this sequence moves towards VNP. It moves closer to it with every iteration. And the same result holds for the Hubs force vectors as well, for that sequence. Okay. So this is how we can actually talk about the convergence properties in the case of for the Hits algorithm. Okay, so this brings us to the end of the discussion on feedback-based centrality approaches. Now, there's yet another kind of centrality approaches, which are path-based. We'll take a look at that in the next lecture. Thank you.